8.9 is that example that I mentioned at the beginning, that's about the Schumann resonances. So the idea is that now you have a, if you look at it in the wheel of a resonator, the Earth is conducting, is actually pretty good conductor because we are, I mean, we usually wire tie up to the Earth, then it's called grounded, it's considered conducting, right? And the ionosphere is also a conductor. You have ionization, it's not a very good conductor. It's just partially ionized. So the sigma in both the Earth and the ionosphere is not that good. But if you still look at this as a resonator, so you have bounded by these two surfaces, and within is air, so it's a medium, although you pretty much pretty close to vacuum. And then it can excite electromagnetic field within the Earth. Usually the excitation is due to lightning. The lightning will excite wave. Okay, so that is, you can look at that as a resonator. The most interesting thing is the lowest frequency mode, the lowest frequency, the frequency, and then the intensity of those modes. This the lowest frequency are what we call the Schumann resonances. Okay, and we can consider which kind of mode will give you lowest frequency by consider the TE mode and TM mode, right? And we can define some dimension first. So the length of the air injection, I think in this section defined as this A factor, called A. We suppose people usually keep it large, capital R, but in the section use this A, right? Yeah, I used to use A. And then on top of that, the distance that go to the ionosphere is called H. Right? Obviously, A is much greater than the distance to the ionosphere, although that is pretty long distance in our perspective, but compared with the radius of it, it's still small. Okay. Now we can consider the TEMO and TMO. So the TMO, you have the psi. The psi is the field along the z direction, which in our case is along the radial direction. If you look at that, so this is z, but you can look at any direction. This is just along the radial direction. The psi is either the I mean, for TMO, the psi is the electric field, right? Psi is the psi is EZ or ER, right? And the boundary condition for that one is this is the ER mode. You can go back to the TM, and we talked about resonated. The TE mode is given by, but this is TM mode. TM mode is in 8.77. Or I mean, 8.74 is the psi is given by cosine P pi 0 d. Right? We can still approximate it like that. So it's partial psi, partial on the side, not on the side, on the top and the bottom side. So the boundary condition is partial psi, Z or partial R at the two surfaces, R equals to A or A plus H. That is 0. So it's cosine. So it's a cosine. So this cosine p pi c over d. And in our case, it's p pi r. Or you can define a c value is from 0 to h. So this is h, right? And so p is from 0 to 1. So you only require the derivative to 0. So you can take the 0 value. The 0 value, then cosine is just 1, because cosine 0 is 1, right? So then, so that's just like the radial electric field outward in that case. So the wavelength of this, the wavelength of the mode is not along this radial direction. The wavelength is we're looking at fundamental or lowest frequency. We're looking at the longest wavelength. In that case, for periodic boundary conditions, like what we are talking about. So in the other two directions, periodic going around this the Earth. So you should have waves that going around. So in order to that is a wave, then you have a wavelength roughly the order of the radius of the Earth. Okay. Then the frequency of these waves, we are just estimating that yet. The frequency times wave omega times wavelength, the speed of light, close to the speed of light, because this is very close to vacuum. C or C over A. Right. So for TMO, the frequency is of the order of C over A. For TE mode, the psi is the electric field is BR. It's the magnetic field, right? And then the perfect boundary condition is BR should be 0. So at the two surfaces is 0. Actually, at the top and the bottom boundary is 0. So it's given by instead of cosine is sine, right? And p does not take 0. You cannot take 0. So at least you have the pi 0 over h sine, right? So you have for TE mode, so you need the wavelength at least like h. So lambda is in that case omega is c roughly. The C of h is obviously because of A is much greater than h, much greater than C of A. Okay, so all the lowest frequency modes are given by the TM. The TMO depends on the mode structure. In this periodic direction, you can have a series of modes. And to solve that, you basically need to solve the three-dimensional Laplace equation, actually Helmholtz equation. Remember the wave equation that we choice was gamma squared times sine. You still need to solve something like that for the speaker geometry. So this transverse one now is just the theta and phi part of the Laplace, right? And the theta and phi part, you remember our discussion in electrostatic that will involve in spherical geometry, you involve this Legendre polynomial. Remember that Legendre polynomial or Legendre function. Okay, and you solve it, which we won't do that. It took a while. Jackson has at least a simplified treatment of that. And what you get is ultimately it's let's see if we have some. I think 8.105. I'm ignoring all these modes that with the C of H. So all the lowest mode is given by this C of A, this aspiration multiplied by this times alpha 0. that you get from the general polynomial. So obviously L cannot take zero. The general polynomial has L equals zero, but L equals zero is a total symmetric mode. And for resonator side, if this E R is just total speaker symmetric the electric field, then see that there's no transverse. We call there's no transverse field, and there's no oscillation. So so L will take just start from 1 to right, and so that this frequency can be measured. The fundamental mode. I think Jackson has a figure for that. And the feature of that is that the DSDs are very leaky. The profile of the line width is very large. So the fundamental mode is the width is roughly equals to the frequency, right? So, so the Q is very small for this. So this maybe L equals to 1, and then L equals 2, that's another one. And L is very noisy. Look at the graph, very noisy. Right. And but you actually measure this the peak. It's roughly satisfying this ratio or this dependency on L. At least it will be different from just multiple or integer for small L only. But for large L, the data will be very noisy. And so that actually can be done. You can actually measure, although the measurement takes some, I think, some special kind of measurement. It's not straightforward to measure the Schumann resonances because of the low frequency. The frequency is really low. If you look at the graph, these are in hertz. The fundamental mode maybe less than 10 hertz. So it's really small, really low frequency. And the wavelength is long, it's not that easy to measure. I mean, people are still working on that. Yes, some people still do research on human resonance. We can have some application because like you can measure the width, which involve the Q and the Q related to delta related to the signal. So it has some dependency on the conductivity, and the conductivity. So you have the ground conductivity, and then the conductivity of ionosphere, which is obviously an interesting quantity to measure. So there's some information on the overall conductivity of the ionosphere by the Schumann resonances, and also the height or the string of the spectral line depends on the activity, because the Q is so small. Then in order to maintain a profile, you constantly exciting wave, and the excitation is due to lightning, and the fact that it's always a Schumann resonance is because there's always lightning somewhere in the earth. You always have some lightning, but then the activity level is an indication of how the earth responds, or how the climate change, or especially the temperature. Usually when we have higher temperature, you have more this weather events. So the overall temperature is an indication. I mean, the intensity can be an indicator of the overall temperature of the Earth. So that's also interesting. But obviously, these things are not as accurate as other measurements of the global temperature. Nowadays, you have a satellite looking at the spectrum, all the spectrum from using look at the Earth and deduce a more accurate temperature from using the spectrum rather than the Schumann resonance. But anyway, that's I mean yeah, other applications. All right, so that's an example of resonant